everyone, I am Jamaica Rose Bilibinafilie, and together with my groupmates, we are going to report Chapter 8, Remote Sensing Techniques in Data Assimilation for Hydrologic Modeling. Water. It is a vital natural resource. Society is in constant need of adequate estimates of available water supply and expected demand, and timely knowledge of potential occurrence of extreme hydrologic events such as floods and droughts. Our relationship with water is complex and delicate. We depend on regular access to clean water for sustaining life and other way of life. Accurately and frequently characterizing various forms of water in the Earth's hydrologic cycle enables improved understanding of this relationship. As we all know, water plays an important role in our lives, especially to us humans and also to the other living creatures. In this chapter, we will know more on how the different hydrologic modeling will be observed using the techniques and satellite systems. Remote sensing theory. Remote sensing can be broadly defined as obtaining observations without the sensor actually being in contact with the object being sensed. Each component of the hydrologic cycle has its distinct signals and respond to different regions of the electromagnetic spectrum. So, kapag sinabi natin remote sensing, ito ay isang process kung saan process of detecting and monitoring physical characteristic of an area. Kung saan na-measure ito use through reflected and emitted radiation, typically from satellites and aircrafts. So, sa pamamagitan ng mga satellite platforms na measure ang electromagnetic at nakakapagbigay ito ng mga necessary basis for the retrieval of a large number of geophysical parameters, including digital elevation models, precipitation, surface temperature, evapotranspiration, soil moisture, runoff, groundwater storage, land cover or use, and various snow, ice, and vegetation-related characteristics. Gamit yung mga satellite na may measure niya yung mga hydrologic events or yung mga hydrologic modeling. So, meron tayong iba't ibang klase ng mga ginagamit upang ma-observe yung mga hydrologic modeling. First, multispectral scanner. Measure the spectral reflectance of the Earth's surface over a variety of narrow bands. So, kapag sinabi natin multispectral, ito ay isang scanning system kung saan nakokollect nito ang data over a variety of different wavelengths ranges. Second, thermal sensors measure the emitted radiation in the thermal portion of the electromagnetic spectrum. Kapag naman sinabi nating thermal sensor, ito naman ay ginagamit para sa pagdetect microwave sensor that acquire observation in the longest wavelengths of the spectrum, 1 mm to 1 meter. Yung mga microwave sensor naman, ito ay ginagamit para ma-measure ang atmospheric profiles and also to determine the water and ozone content in the atmosphere. Remote sensing in hydrological sciences. Historical perspective. Through there had been numerous aircrafts and ground-based surveys in mid-1900s. The true start of global remote sensing in the support of the Earth sciences and the hydrology can be linked to the launch of the system such as Landsat, launched in 1972, and the Advanced Very High Resolution Radiometer AVHRR, launched in 1978 by Holben Loveland. So, yung remote sensing ay madami siyang ginagamit na mga satellites kung saan mas nakakatulong ito upang mas maunawaan natin kung ano yung mga iba't ibang hydrologic events na nangyayari sa ating mundo. Soil moisture measurements, which were previously derived using C negative or X band data, are now available from two L-band missions: soil moisture ocean salinity and soil moisture active passive, launched in 2009 and 2015 respectively. Building upon the legacy of the Tropical Rainfall Measurement Mission, the Global Precipitation Measurement Mission was launched in 2014, which provide global coverage at 10-kilometer resolution within 3 hours. So, meron tayong iba't ibang remote sensing methods and techniques. Soil moisture. Soil moisture is one of the smallest components of the hydrologic cycle. However, it plays an important role in the terrestrial cycle. Dahil nga smallest component siya, ginagamitan ito ng microwave observation that acquire the frequency of 10 GHz or mas mababa pa dito. Advanced Microwave Scanning Radiometer for EOS. So, ito naman yung mga iba't ibang klase ng mga satellites na ginagamit. It is a 12-channel 6-frequency passive microwave radiometer aboard NASA's Aqua satellite designed to study Earth's water cycle and precipitation rate, cloud water, water vapor, sea surface wind, sea surface temperature, ice, snow, and soil moisture. So, ang Advanced Microwave Scanning Radiometer or AMSRE ay ginagamit ng NASA para malaman yung mga water cycle and precipitation rate. Yung mga nangyayari sa tubig. Soil moisture and ocean sanity is a satellite which forms part of ESA's Living Planet program. It is intended to provide new insight into Earth water cycle and climate. So ito namang SMOS, nakakatulong to para malaman natin yung mga climate at iba't ibang water cycle. Advanced Microwave Scanning Radiometer AMSR2 provide almost coverage of the Earth every 2 days, and technically it is very similar to its predecessor AMSRE. It offers a few additional features such as an extra 7.3 GHz channel for radio frequency interference mitigation and improved calibration using the hot load. So, ang AMSRE ay mas pinaganda, in-upgrade para mas mapadali yung pag-measure natin sa iba't ibang hydrologic events or pag-observe natin. Soil moisture active passive. It provide global observation of soil moisture and freeze thaw at unprecedented spatial resolution. It will also provide an L4 surface and root zone soil moisture product, which will be generated by integrating the SMAP base retrievals into a land surface model driven with meteorological forcing data. So makakatulong ito sa pag-provide na observation through soil moisture. Mas mapapadali nito ang pag-observe natin sa iba't iba sa soil moisture.
So the next is groundwater. So ano nga ba kapag sinabing groundwater? Groundwater is the water present beneath Earth's surface in rock and soil, pore spaces, and in the fractures of rock formations. So kapag sinabing groundwater, makikita ito sa Earth surface, yung mga tubig yan na nakikita natin sa paligid, groundwater yon. About 30% of all readily available fresh water in the world is groundwater. So yung mga nakikita natin na tubig yan, 30% nun is fresh water. Next is the Gravity Recovery and Climate Experiment or GRACE. Small spatial and temporal gravitational variations can be detected by GRACE by measuring the slight alterations of the orbits of the twin spacecrafts. So, yung GRACE, siya ng kahit maliliit na galaw dito sa Earth, ay na-detect niya. Small changes in the Earth's gravity caused by gas, liquid, or solid mass transports are reflected in the Earth's gravity field and recorded by GRACE. Yun, nare-record niya kahit mga maliliit lang na galaw or yung maliliit na changes sa gas, liquid, or solid. Next is surface temperature and vegetation's indices. Moderate resolution imaging spectroradiometer or MODIS. The MODIS provides a total of 44 data products related to the land, ocean, and atmosphere, including measurements of surface temperature, normalized differences vegetation's index or NDVI, and leaf area index LAI. MODIS is on board both the Terra and Aqua satellite platforms, which were launched on December 1999 and May 2002 respectively. So, yung MODIS po is, nagme-measure siya ng mga nagkukuha siya ng mga data na related sa oceans, land, at atmosphere. Mini-measure niya po yung temperature nun. Next is Geostationary Operational Environmental Satellite or GOES. TS and several other products, regions, rainfall rate, snow, cover relevant to monitoring a number of hydrological processes are estimated using observation acquired from the GEOS or GOES rather. So ito, nagme-measure din ito katulad nung MODIS. Yung GOES. Like MODIS, nagme-measure din siya ng mga nangyayari dito sa Earth. Next is precipitation. Precipitation is a key component of the hydrologic cycle and can be estimated using data from various wavelengths. So, di ba napag-aralan natin yung precipitation sa previous report ng mga classmates natin. So, yun po ang precipitation. Key component siya ng hydraulic cycle and can be estimated using from various wavelengths. Next is TRRM, which is the Tropical Rainfall Measurement. So, TRRM was launched in 1997. TMI has an orbit that extends from 35 ON to 35 OS, limiting the coverage to the tropics. The sensors on board the TMI have 9 horizontally and vertically polarized channels with frequencies from 10.7 JHz to 85.5 JHz. The TMI completes an orbit every 91 minutes, making 15.7 orbits per day. Thus, the TMI overpasses any particular area at different local times each day, providing one or more observations in the target area daily. The TRRM repeats its orbital cycle every 42 days, passing over the same spot at the same local time. So, itong TRRM, ito yung satellite na umiikot-ikot sa Earth na siya, dito. Siya yung nagde-detect ng mga rainfall. Kaya nga sinabing the Tropical Rainfall Measurement. Siya yung nagme-measure ng mga rainfall. Next is GPM. The GPM mission launched in 2014 is designed to produce a variety of precipitation products. It includes a dual frequency precipitation radar or DPR and a passive-based GPM microwave imager or GMI. The DPR collects co-line observation at Q-band and Ka-band, while the GMI includes 13 microwave channels ranging between 10 and 189 JHz. The combination of these two instruments and multiple observational frequencies allows to simultaneously estimating different rain rates and determine the size of the precipitation particles. GPM covers the Earth from 65 S to 65 N, or 65 degrees south to 65 degrees north, and is capable of providing precipitation and estimates every 2 to 3 hours. The satellite flies at an altitude of 407 km in a non-sun synchronous orbit. So next is LiDAR, Light Detection and Ranging, or LiDAR. It is a remote sensing technique that measures distances or ranges to the Earth by sending pulses of light. So, Jensen 2007. LiDAR systems are most often mounted on aircraft platforms and typically consist of a laser, a scanner, and a GPS receiver, which enables the collection of precise, high-resolution, three-dimensional information about the Earth's shape. Campbell 2002, the most significant application of LiDAR in hydrology is its use for the generation of DEM, or DEM. So, yung LiDAR, yun yung ano siya, ng parang negative na color na nag-detect sa Earth. Yun po yun. Yung parang kapag sa phone, yung kapag ginamit natin yung filter na negative is yung ang makikita natin ay ibang color or colorful. So, next is data assimilation theory. Data assimilation is the process of combining information from models and observation into estimates of the state of a dynamic system. So, Richel 2008. In this case, we are generally concerned with estimating mass and or energy states of the hydrologic cycle from remote sensing data. The model is continuous in both time and space between remote sensing observation and also allows us to extrapolate information in remote sensing observations to parts of the hydrologic system that are not directly observed. So, yung data assimilation theory is measurement siya or nag-estimate siya ng mass or energy states of the hydrologic cycle. So, the most form of the data assimilation equation is, ito yung formula ng data assimilation. So, which is, where P denotes a probability distribution, X is the time series of the dynamic states simulated by the mode over the entire simulation period and domain. Say are all of the remote sensing observations available in that domain, and U are the model forcing data or boundary conditions. In general, it is assumed that any forcing data contains errors, so it is necessary to integrate over the uncertainty in this data.
Estimating the prior and likelihood, the prior distribution over the state system is given by P and M. This is obtained simply by running the model M with some recognition that the model is not exactly correct, whereas accurate as they are precise. There would be a need for satellites. The most common way to do this is to add some Gaussian error to the model states at each time step. So, yun nga, kung hindi naman kailangan ay kung hydrology weather daw ay kung accurate at mas okay, hindi na kailangan satellite. So, common way lang daw dito para this common way is to add some Gaussian error to model states at state. And sample of the Bayesian likelihood distribution denoted obtained by sampling noisy observation process that may be time dependent. So formalize y sub t is equals to h sub t, quantity of x sub t, and u sub t plus a sub t. So next is approximating the full Bayesian solution. Bayes theorem is infactable for all but the simplest models and the most common methods for approximating a solution to involve one or more of the following. Number one is independence assumptions. Number two, orational or sampling approaches. And 3 is parametric approximations. Filters versus routers. The biggest practical issues is that the posterior distribution has dimension equal to the product of the size of the domain by the number of states in the model by number of times steps. This product is generally very large. To reduce the size of the inference problem, we can use the macro property of equation 82 and check the present state as independent of future observations. So at each time step state, full solution is approximately by the series step solutions like so. Base theorem always provides a way to calculate the probability of hypotenuse on its prior probability, so also known as or simplest way, simplest known as formula for probability of causes. And approximating the full Bayesian solution, ito parang ito yung formula. So, hindi ko siya paliwanag. Medyo hindi ko siya magets. So, skip na tayo dyan. Variational versus ensemble. So far, we have sample the probability distributions on the right hand side of equations 8.1 and 8.4, and we have used a filtering strategy to reduce the complexity of the problem. We still need a way to approximate the integrations over the state distributions and forcing data. So ito, where P is the covariance of P, and R is the covariance of E. Assume A prior. For linear models, this minimize at. And the next is where Q is the covariance of model observation. Depends on P. And S is the covariance between X and Y. More generally, equation 8.5 can be minimized using the iterative method with or without derivatives. So, yan yung sa baba. And then, next is parametric versus non-parametric. All methods discussed earlier rely on parametric assumptions about model and observation operators and their associated uncertainty distributions. So, sa parametric, ang parametric is more popular and considered to be more powerful statistical test than non-parametric test. So, yun lang ang pagkaiba nila is parametric is more powerful than non-parametric. And kailan ba natin ginagamit ang parametric test? So, kapag daw ang parametric test or data has a normal distribution and measurement scale is interval or ratio. So, yun. And samples of the posterior distribution at each time step are obtained by reweighting an ID Monte Carlo sample of the prior with probabilities proportional to. So, yun ulit, formula. Kung basa, makita. So, natin skip na ulit. Balik ko siya magets formula. And next is dealing with bias. When we use certain parametric data assimilation techniques, like then bias in either M or H will result in bias in posterior states. Estimates there are currently two ways to deal with this. Number one, yung two ways to deal with this, Kumar et or ano lang. Una is mapping observation to the model. Climatology. Number two is calibrating the model to the observation climatology. So CDF matching, empirical CDF with infinite precision delta y are constructed for individual dimensions of both modeled and observed y. So CDF, quantity of y mean or y sub mean plus delta y is equals to 1 over t and notation t over sa baba niya is t is equals to 1 multiplied by 1 sub 1 or sub t um, less equal to multiply sa y sub min plus delta y. So where y min is the minimum collectively among all retrievals z, and model predicted retrievals y is histogram b number, and CDF is either the model or observation cumulative sensitivity functions. Observations are then translated into the model climatology using linear interpolation. So yun na, formula ulit, haba. Next siya next na ulit. And analytical solution considers only the first two moments of the cumulative density functions. So yun ulit sa baba. And next na ulit. And last is simultaneous state and parameter estimations. If you wish to attribute the majority of variance to the dynamic model, and observations can be used to simultaneously estimate model states and parameters. So, yun lang po.